One more connection. This wheel of serious injury here. If I get it sped up here, so that its omega by right-hand rule is right out along that post, well, this wheel is weighted so that it doesn't want to slow down. So the spin rate stays the same. Now the spin rate tells me how long the omega vector is. It's not speeding up, it's not slowing down. The omega vector is not getting longer, it's not getting shorter. It always points out along that bar. Is the omega vector changing?
Yes.
Yeah, it's changing direction. And because the omega vector is not getting longer and not getting shorter, the alpha cannot be along the direction of omega or opposite the direction of omega. The only direction left is perpendicular to omega. So I have a little representation here. Let me spin this up again. Again, if this were Harvard, we'd have a machine or a grad student to do that. Okay, so the omega vector is always pointing along the red arrow, and it never gets longer or shorter. The alpha vector is the blue arrow. It's always 90 degrees to the red arrow. What does this remind you of in the linear kinematics case? Talk to your neighbor. Talk to Nimrod. Okay. Brave soul, what does it remind you of? Raise your hand.
Centripetal acceleration.
Centripetal acceleration when you're going around in a circle. Okay? If you put cruise control on and you go around in a circle, you don't change the length of your velocity vector. But you are changing the direction of the velocity vector, and that means your acceleration vector has to point 90 degrees, which in a circular case is towards the center, and hence we call it centripetal or center seeking.